Hi guys, welcome back to the channel. Today we'll talk about consistent hashing, which is a very important concept in system design. The example we're going to look at is a distributed caching system. So let's say we have four servers, S0, S1, S2, and S3. We're going to use these four servers to cache data. So whenever a piece of data comes in that we need to cache, we should cache it in one of the four servers over here. And our system should be flexible enough so that in higher traffic spikes, the number of machines increases. And when we are not serving that much traffic, we can reduce the number of machines to save us some cost. So the first thing you need to know is when a piece of data comes in, how do you know where to cache the data? And how do you know which machine to look into for a given piece of data? So for example, let's go with user ID as our input data. So whenever a request comes in with a particular user ID, how do you know which machine should we put the data in for that user? Similarly, when a request comes in for asking for data for a particular user, how do you know which machine to look into? So right now in the system, we have four machines. So when a request comes in, we should be able to tell deterministically that if we cached the data before, it should be in this one machine. We shouldn't need to look at all the machines and see which machine has our data, because that is very inefficient. So to deterministically be able to tell where your data is, you need something called a hashing function. So a hashing function is just an ordinary function which can take in an input and deterministically give you the output. So for every input, it is always going to give you the same output. In this case, whenever we have a set number of servers, the function should always give you the same output given a user ID. So if you look at the example over here, for user ID 44, if you're using the hashing function over here, it's going to give you the number 0, which means in server 0. Similarly, for 15, you're getting 3. For 21, you're getting 1. For 8, you're getting 0. And for 66, you're getting 2. So as long as the number of machines are not changing, you're always getting the same number through this function. So the number 4 over here, this is the number of machines you have. If we had 10 machines, we would do k mod 10. If we had 20 machines, we would do k mod 20. So the number here is pretty much the number of machines that you have, which, remember, is elastic, because depending on your traffic, you might either need to scale up the number of caching machines or scale down the number of caching machines. So to summarize, if we're using the function where we're modding the input, which in this case is a user ID, by the number of machines, it should give us the server where the data lies in. So let's look at this one last time. If a request comes in for user ID 44, we pass 44 to the function. We do 44 mod 4, which is returning to a 0. So the data should be in server 0. So in this machine over here. Similarly, for 15, 21, 8, and 66, the function should tell us where to look into to retrieve the cached data. Now, let's talk about the obvious thing that is going to happen very time soon, which is your website is going to get a huge spike in traffic. You'll be serving way more requests than normal. And to serve the request sufficiently, you would need a higher number of machines to cache the data in. So in this example, we're going from 4 machines all the way to 7 machines. So now let's see how, using the same hashing function, we can serve these requests. So for user ID 44, now instead of doing modding by 4, we're modding by 7, because our number of machines just increased from 4 to 7. That is giving us server 2. For 15, it's giving us server 1. 21, it's giving us server 0. 8, it's giving us server 1. And 66, it's giving us 3. So we're doing the exact same thing, except instead of modding by 4, we're modding by 7, because our number of caching machines just scaled up from 4 to 7. So what is the obvious observation over here? All the mappings that you see over here, they have changed. So if you look at a comparison between the two, for the user ID 44, with 4 machines, our data was in server 0, but now with 7 machines, our data is in server 2. For user ID 15, it was in server 3, now it's in 1. For 21, it was in 1, now it's 0. And for 8 and 66, similarly, the machines have changed. So just because we increased our number of servers from 4 to 7, all our mappings have changed. So right after this scaling up happens, so we go from 4 to 7 machines, all the requests that are coming in during this huge traffic are going to get a cache miss, because let's say the user ID 44 comes in, and we try to look into the new machine S2 for the data, and we don't find it, because previously the data was in server 0. Similarly for 21, the request comes in, we take a look at server 0 where the data should be now, but it's not, because before it was in server 1. So we're going to get a cache miss for 100% of the mapping. So all the data we cached before pretty much needs to be cached again, because the assignment is all over the place. So this is where the concept of consistent hashing comes in. Consistent hashing is a way where hashing function is not going to reassign all possible input-output only if the number of machines changes. So previously, as you saw, when we changed from 4 to 7 machines, all the mappings changed. But using consistent hashing, you can be assured that whenever there is a scaling up or scaling down, all the mappings do not change, so that you don't get this huge spike of cache misses. So let's look at how consistent hashing works. So the first thing you do is the range of values that your hashing function can produce, you organize it in a ring over here. So let's say the minimum that your hashing function can output is 2 to the 0. So you put it over here, and then you go clockwise and you pretty much like lay the numbers, like you put 2 to the 10 here, 2 to the 20, 2 to the 30, and then you circle all the way back over here. So it's going to be from your min to max that your hashing function can produce. You organize it in a circle. Now, once you organize it in a circle, you pretty much put the number of machines you have on the circle. So let's say you have 4 machines. So you evenly distribute your ring of numbers. You evenly distribute the number of servers you have in this ring of numbers. So you put S0 over here, 1, 2, and 3. So now let's say a request comes in. How do you find on which server your data lies in? So the steps are pretty clear. So let's say user 44 comes in. Let's just do, so let's say we have user 44, which is our input. So for that input, what we're gonna do is we're gonna find HK. So we're gonna put it through our hashing function. And let's say once we put it in the hashing function, we get this point over here, whatever number is here in the ring. So that's where 44 should go to, right? So you come to that point, we're doing step 1 right now. So you come to that point, and then you read clockwise. So you come here, and then you're reading clockwise until you find a server. So if we start reading clockwise from here, the first one we hit is server 1. That means your data for user ID 44 should be in server 1. If we go through another example, let's say our number is 20. Let's say user ID 20, and we want to know which machine the data for user ID 20 lies in. So you put it through our hashing function hk, where k is going to be 20, and it spits out a number. And let's say that number in this line over here, that number that your function is generating is over here. So you start from here, you go clockwise till you hit a server. So if we start from here, we're going clockwise, we're hitting server 2. That means your data is going to be in server 2. So just by arranging the key space in a circle like this, and then putting the number of machines we have evenly across the circle, we get a lot of benefits, which we're going to find out in the next few minutes. So just to drive this home, if you have an input, which in this case is a user ID, you put it through the hashing function, you get whatever output. Let's say the output is just like B that you get. And then you look at the ring over here, you look at where's B, because all these are numbers, right? We're starting from 2 to the 0, we're going to do the 10, 20, 30, and then we go back to 2 to the 0, right? So let's say the input comes in, we put it through the function, we get the answer B. So we find where's B in the ring. Let's say B is over here, right? And then we start counting clockwise. So we go up, up, up until we hit a server, which in this case is server 3. So the request that came in, the data for that request lies in server 3. So just for a refresher, this is what we had in the previous slide. So we have 0, 1, 2, 3. Now what happens during scaling up? Let's say we have 2 new machines, 4 and 5. Just like before, we were getting 3 new machines and going from 4 to 7. Let's say we're going from 4 to 6 now. Right? So in this case, we had S1, S2, S0, S1, S2, and S3. Now we have 2 new machines. So we try to still just add the machines evenly instead of just putting 2 next to each other. So let's say 4 is here between 0 and 1, 5 is here between 2 and 3. So these are like the 2 new machines we added. So we did the same thing we did before over here. So before we had 4 machines and we add them over here. So now what we're doing is the 2 new machines we got, 4 and 5, we're just trying to distribute it as evenly as we can. So we put 4 somewhere between 0 and 1 and 5 somewhere between 2 and 3. So now what happens? So remember how before, whenever we were adding new machines, so when we went from 4 to 7, all the mappings were changing. So no matter which user ID or request came in, we were needing to get the data from the disk because it was giving us a cache miss. So let's see what happens now. So given we added 2 over here, any user ID, so let's look at S4, right? Any user ID that is going to return a hash output in here, the assignment for those are going to be changed. So let's go through an example, right? So let's say we have a new request that comes in for the user ID 12, right? So we have user ID 12 that comes in. We put them through the hashing function. And let's say the hashing function spits out the number 2, right? We look at the number line and let's say this place in the line is 2. So we follow the same recipe, right? So we get 2. We start going down in a clockwise direction until we hit a server, until we hit, in this case, we hit server 4. So 2, the data for user ID 2 is going to be in server 4. What would have happened previously? Let's see. If we were in the previous assignment, and if we got the user ID 12, just like we did here, we put it through the hashing function, and it returned to us 2. 2 is over here. We go clockwise, and the nearest one we find was server 1. Whereas now, after the scaling up, it's getting server 4. So the mapping for user ID 2 has changed. However, what's happening when a data, let's say we're doing it again, this time for user ID. So let me just delete these. Yeah. So let's say we're getting it for user 30 now. We put them through the hashing function, and let's say the hashing function is giving us 120, right? So where's 120 approximately in this number line? Let's say 120 is over here, right? Let's say this is 120, right? 120. So you get the number 120, you start reading in a clockwise direction, and you hit server 2. So the data for user ID 30 is in server 2. What was happening previously for the same user? So let's say we were doing user ID 30, putting them through the hashing function, getting the number 120, right? 120 was somewhere here. We were approximating. There you go. And then we started reading in a clockwise direction until we hit the server, which is S2. So this is the fun part. So after the scale up, our data for user ID 30 is in server 2. Even before the scaling up, when we had 4 machines, the data was still in server 2, which is very different from what we used to get before, where when we scale up, we were getting 100% change of all the mappings, right? So all the mappings were changing and all of them were giving a cache miss. But just by arranging the key space in a circular manner and then going through the steps, the 4 steps over here, we are making sure that not 100% of the incoming request is going to give you a cache miss, just like you saw with this example. So only a fraction needs to be remapped. So the next question might be, so which exact numbers are going to need the remapping? So if you look at this carefully, so I'm going to delete these 2 over here. Give me 1 minute. All right, let's just skip that. All right. So any number the hashing function generates between this, so between S0 and S4, is going to have a new mapping. That's because any number that fell in this segment, the yellow highlighted area that you see, is going to server 4 now. Whereas before, when server 4 was not there, if we followed in a clockwise direction, we would have come to server 1. So it's only this fraction over here. Similarly, the yellow highlight you see over here, any number that was falling in this range is going to go to server 5 now, whereas before it would have gotten to server 3. So you can see any number that was going to fall here before was going to go server 3, but now any number that's falling here is going to server 5. Similarly, any request that's falling over here is gonna go clockwise to server 1, but any number that's falling over here now is gonna go clockwise to server 4. So those 2 are the only one that's changing. Apart from that, no matter where your number comes down to now, so let's just change colors over here, all the mappings over here, all the mappings over here, none of them are changing. You're gonna go to the same servers just like you were before. So the only mappings that changed are this and this, which is a very, very big improvement from before, where we were getting 100% mapping change and all the requests that were coming in was getting a cache miss. So now let's look at one of the most common problems with consistent hashing. So we saw like the benefit we get out of it, which is not all the mappings needs to be changed. So we significantly reduce the number of cache miss. But this can still get tricky if your assignment is not correct. By that, what I mean is if you're not putting the servers in the correct place, you might not get the best remappings. And also, if your requests are always falling in the same part of the circle, then you might run into other issues. So let's see one of the biggest problem related to that. And that would be the hotspot problem. So let's see what the hotspot problem is. Let's say you do the first step, which is you organize your hashing function's key space in a circle, and then you put your 4 servers evenly between the key space, right? But let's say just the way your user requests work, most of the requests that are coming into this function, they're spitting out a number in this region over here. So let me change the color. So the number it's spitting out is over here. So what's the problem when that happens? The problem when that happens is for every request, the data is going to S1, that's server 1. So this is something called the hotspot problem, because your requests are not even at all, they're lopsided. So all your requests are always coming in this space only, and all your data is going to S1. This would mean, firstly, is you won't be able to keep enough data in cache, because S1 is just one machine. You have multiple other machines that are just empty right now, and all your data is in S1. So you'll have an issue with space where S1 is going to be overburdened. You also have an issue with request timing, because S1 is going to get overwhelmed. It might get DDoSed because every request that's coming in is pinging S1 for the data, whereas all the other machines here are just chilling because they don't have anything. So that's very bad distribution, and doing it this way, yes, we might get around the mapping issue, but this is not sustainable either. So what can we do about that? So let's see. So the solution, or maybe the workaround you have, is something called the virtual nodes. So let's just go with the concept of having 4 nodes, right? So we have S0, by nodes I mean machines. So we have S0, S1, S2, and S3. Just like before, we have 4 machines. But remember the hotspot problem, where we were thinking, what happens if all the assignments were coming here, right? So a good way to solve this is we just forget about the rest of the circle, just focus on this part over here. So what we do is we further divide this one segment into like 4 other parts. So let's just say we have 4 machines, right? So let's say we put 4 virtual machines over here. I'll explain it in a bit. So we have S0 prime. This is not actually a machine. This is just a concept we're making up. We're saying S2 prime and S3 prime. So what this means is if a request comes in, let's say, let's just change colors over here to make it more legible. Okay. So remember what was happening before. If there was a request coming in over here, actually, let's just use a pencil and give it a color of red. So if a request was coming in over here, that was going to S1, this was going to S12, this was going to S12, this was going to S12. So all of them are going to S1. But by putting this fake servers over here, once again, these are not actual servers. These are just concept, like logical. These are just logical servers. They're not actual machines. We're just making it up right now. So if we have 0, 1, 2, 3, we're making up 3 servers and naming them S0 prime, S2 prime, and S3 prime. Now let's say a request comes in, right? So let's do it green over here. So now instead of going, so let's go clockwise, and the first server we hit is this S0 prime, right? And remember I said this is not a real server. What this means is we're telling this system that act as if this is a real server and then route the request to that server. So if you hit S0 prime, you just cache the data in S0 because we're kind of like making a duplicate copy of S0 prime. Similarly for S2 prime, let's say we have a request that comes in over here. We go clockwise and we hit S2 prime. S2 prime is just a logical representation of S2. S2 over here. So if we are hitting this part, then we say just store the data in S2. Similarly, if we're getting a request over here, we go clockwise and we hit S3 prime. That means just put the data in S3. So by segmenting this one part and giving it these like fake replica servers, which are not physical machines, they are just logical units of the actual servers that we have. So for data to end up in S0, the user ID, the hash output doesn't have to fall here. Because previously, the only way the data could go to S3 is if the request was somewhere here, right? And that's the main reason we were running into the hotspot problem, because every request that's coming in here is only going to S1. So if majority of our requests are falling here, then S2 and 3 are going to be totally free, but S1 is going to be very, very busy. Hence, it's going to be a hotspot problem. But by dividing the segment into these virtual nodes, what we're saying is, I know there are no actual machines over here, but there are these virtual machines called virtual nodes. So put them in there. So if I get a request over here, instead of going all the way and storing it in S1, go and hit the first virtual node, which is S0 prime, which is the same as saying the data should be in S0. If a request comes in here, we do S2 prime, which is the same as putting the data in S2. This way, all the requests that are here are not ending up in S1, so you're avoiding the hotspot problem. Now the data is going to be distributed amongst your 4 servers, even if your hash function is very bad and it's always spitting out a number in this region. So the ones we made up as 0 prime, 2 prime, 3 prime are what we call virtual nodes. They are just a logical representation, and they're not the actual machine, but they act as if they're an actual machine, because when we're counting clockwise and we hit a virtual node, we stored the data in the actual machine corresponding to that virtual node. So for S0 prime, we're going to be storing the data in S0. 2 prime, we're going to be storing the data in server 2. 3 prime, we're going to store the data in server 3. So if you look at the whole key space now, we're pretty much going to do the same for all the segments. S0 to S1, normally all your requests would have gone to S1, but now we are also adding 0 prime, 2 prime, and 3 prime, so that any request falling over here gets evenly distributed amongst the 4 servers, which are going to be 1, of course, then 0 prime, which is 0, 2 prime, which is 2, 3 prime, which is 3. Similarly, for this section, let me just change colors. For this section, previously all the data would have been going to S2, but to get over the hotspot problem, we're giving virtual nodes 0 prime, 1 prime, and 3 prime, so that the data can live in any of the servers, even if there's a hotspot over here. Same for this section, and same for this section. So this way we are guaranteeing an equal distribution, and we won't run into an issue over here. Like if all the requests were coming here, all of them would have gone to S1. Whereas right now, even if all the requests are coming over here, they can go to 0 prime if it's here, they can go to 2 prime if it's here, they can go to 3 prime if it's here, or they can go to server 1 if it's here. So yeah, guys, that's pretty much all there is to know about the fundamentals of consistent hashing. If you have any questions, feel free to put them in the comment section below. I'll get to you as soon as I can. And I'll catch you all in the next one. Bye bye.